Load balancing is the mathematical process of distributing a set of computational tasks across a pool of available hardware resources. Its primary function is to optimize how a system processes incoming requests, preventing any single node from being overwhelmed. The operational objective is straightforward: keep all available compute units actively working. By minimizing processor idle time, the overall throughput of the system increases, allowing the infrastructure to handle higher volumes of traffic. Without an intentional distribution strategy, an application collapses under its own weight. A surge in network requests bottlenecks at a single point of entry, exhausting the hardware's available memory and CPU cycles. As a network scales up, a lack of precise load balancing creates a heavily uneven topology. You end up paying for server clusters where a small fraction of the nodes are dangerously overutilized, while the remaining hardware sits completely idle. Solving this creates a strict architectural tension. To route traffic perfectly, the central load balancer requires real-time telemetry about the exact state and availability of every machine in the cluster. That telemetry comes with a built-in penalty. Querying a server to determine its current workload introduces communication latency. The hardware has to pause processing tasks to report its status back to the balancer. As the volume of incoming requests grows, the constant exchange of state information compounds. The load balancing mechanism designed to prevent system failure becomes the primary bottleneck, slowing the entire network down. To achieve actual scalability, engineers have to move beyond simple static algorithms and design physically decoupled, dynamic hardware topologies that separate decision-making from data delivery. The most common baseline approach is round-robin load balancing. It is a strictly static algorithm, meaning it operates entirely without state awareness. It does not monitor the health or current workload of the machines it manages. This diagram illustrates a basic round-robin topology, mapping 9 incoming requests through a central load balancer and distributing them across a 3-server cluster. The routing sequence is purely cyclical. The balancer forwards the first request to server A, the second to server B, and the third to server C. Once complete, it resets to the top, repeating this pattern indefinitely. This model relies on a rigid technical constraint. It assumes every machine in the cluster possesses the exact same computing power and storage capacity. It also relies on a second assumption. To distribute the burden equally, every incoming task must require a highly uniform amount of execution time. In time-shared systems, this execution time is dictated by the specific time slice allocated by the CPU scheduler to process each task. If those allocated time slices are extremely large, the round-robin algorithm functionally degrades, losing its parallel efficiency and operating as a first-come, first-served model. When task execution times vary significantly, the static model fails. Heavy tasks pile up on specific machines, creating localized hotspots where one server grinds to a halt under a massive queue, while the others quickly finish their light tasks and sit empty. Statelessness optimizes for speed. By ignoring the servers, round-robin incurs zero communication overhead. But that efficiency comes at the direct cost of total ignorance regarding actual network health. Dynamic load balancing adapts to those unpredictable workload fluctuations. Instead of following a blind sequence, it actively queries the compute nodes to gather real-time state information. One of the most effective dynamic methods is the least connections algorithm. It evaluates the entire cluster and deliberately routes the next incoming request to the server currently managing the lowest number of active tasks. Returning to our previous 3-server cluster, we can introduce a time delay. Let's assume a certain amount of time has passed and requests 1, 2, and 3 have completed their execution. The active workload is no longer balanced. Server A is now managing only request 5. Server B manages 4 and 6. Server C is still bogged down with 7, 8, and 9. When request 10 arrives, the dynamic balancer routes it to server A. If this were a static round-robin sequence, that 10th request would have been blindly forced onto server C, pushing a struggling node further toward failure. Least connections prevents this specific overloading scenario. The cost of this targeted efficiency is telemetry. The balancer cannot make these decisions in a vacuum. It has to maintain a continuous stream of connection data from every single machine. In a small cluster, this is trivial, but scaling up to thousands of servers, constant state polling generates a massive volume of internal communication overhead. Every time a server pauses to confirm its connection count, routing slows down. Finding the mathematical minimum across thousands of nodes introduces noticeable latency. Dynamic algorithms ensure high resource utilization, but pull computational power away from the actual workload. The load balancer risks becoming the primary scalability bottleneck. Engineering around this telemetry bottleneck requires a structural shift. The solution is physical decoupling, separating the heavy logic state evaluation from the sheer speed of packet forwarding. This diagram maps a distributed server load balancing architecture. The process is split between two distinct components: the forwarding engine, labeled FE, and the SLB logic engine below it. The forwarding engine acts as the high-speed gateway. Its only job is to move data to a server as fast as the hardware allows. The SLB operates in parallel as the brain of the operation. It monitors the server states, tracks active connections, and dictates the routing logic. The connection sequence operates in distinct phases. Step 1. The client initiates a new connection by sending a TCP/SYN packet directly to the forwarding engine. Step 2. The forwarding engine pauses and queries the SLB for directions. Step 3. The SLB evaluates its connection tables, applies the dynamic algorithm, and instructs the forwarding engine to use server 2. Step 4. The forwarding engine routes the initial packet to server 2, officially establishing the link. From this point on, the system engages a direct flow optimization. All subsequent data packets sent by the client bypass the SLB logic completely, streaming straight through the forwarding engine to the server. By cutting the logic engine out of the continuous data stream, the architecture entirely eliminates the telemetry bottleneck for the majority of the connection's lifespan. The logic engine only steps back in during the teardown phase. When the data flow terminates, the forwarding engine pings the SLB to update the connection count, ensuring the state remains accurate for the next request. Distributed architecture scales dynamically because it divides the labor. It isolates the high-latency decision logic from the high-speed packet forwarding, allowing the network to handle massive traffic volume without bogging down. Hardware optimization eventually collides with software reality. No matter how perfectly a distributed architecture balances the load, it cannot overcome the inherent serial limits written into the code itself. This data flow graph maps the operations of a polynomial equation. While multiple operations can be sent to different processors, specific calculations, like the final additions at the bottom, depend entirely on the results of the multiplication steps above them. They must run sequentially. We measure this efficiency through parallel speedup, which is simply the time it takes to execute a program on a single processor, divided by the time it takes to execute it across multiple processors. As you add more servers to process a task, the speedup initially rises, but eventually you hit a hard ceiling. Once all the independent tasks are distributed, the entire system has to sit and wait for those sequential bottleneck instructions to finish one by one. This limitation is mathematically formalized by Amdahl's and Gustafson's laws, which dictate that the maximum theoretical speedup of any system is strictly bound by the fraction of the code that cannot be parallelized. Routing the data efficiently is only half the battle. Ultimately, absolute system performance is capped by the serial bottleneck of the data itself. Designing a scalable network requires applying these constraints to the correct environment. For systems with highly predictable, uniform workloads, static algorithms like round-robin remain the optimal choice. The trade-off is calculated. You accept a higher risk of node overload in exchange for executing tasks with absolute zero communication overhead. Conversely, for large-scale environments dealing with unpredictable traffic spikes and variable task lengths, dynamic routing through a distributed SLB is required. Here, the trade-off is reversed. You achieve maximum hardware utilization and prevent system failure, but it requires implementing complex, physically decoupled hardware like forwarding engines to mitigate the latency. Sustaining these dynamic environments requires rigorous server monitoring and session persistence, ensuring that related tasks remain properly connected without triggering repeated logic queries. There is no universally perfect load balancing strategy. True architectural scalability is achieved by analyzing the specific volatility of your incoming workload, identifying the serial limits of your tasks, and matching your routing topology to the math.